In this video we're going to work this problem that deals with two different bikes traveling at the same speed. The bikes have the same mass, though they are distributing that mass differently. One bike has a 10 kilogram frame and two 1 kilogram wheels. The other bike has a 9 kilogram frame and two 1.5 kilogram wheels, therefore making the total mass of each one 12 kilograms. We want to model the mass, model each wheel as a hoop and determine the kinetic energy of each bike and see how they compare. Again, when these two masses of 12 kilograms apiece were just traveling in one direction, they would have the same, or if they were just sliding, let's say, in one direction, they would have the same kinetic energy. We're going to see that they don't because we have rotational kinetic energy to consider as well. So here's how we go about doing that. Let's first just talk about those wheels. So we've got the total kinetic energy of a wheel. Well, that's got to be the sum of the translational kinetic energy for that wheel plus the rotational kinetic energy of that wheel, right? As the wheel spins, it's both translating, the center of mass is moving to the side, and it is rotating around as it rolls along the ground. So the total kinetic energy is the sum of the two individual pieces. So we'd have 1/2 times the mass of the wheel times the velocity of the center of mass of the wheel. That's going to be the same velocity as the center of mass of the bike. You can imagine where that wheel is attached to the bike, it's got to be going the same speed as the bike frame. Plus 1/2 times the moment of inertia times the angular velocity squared. There's our rotational kinetic energy term. The problem said we needed to treat the bike wheel as a hoop. So we looked that up on our chart and we get mr squared for the moment of inertia. So we can substitute not only that, this first one won't change, 1/2 mass of the wheel times velocity squared plus 1/2, here's our moment of inertia, mr squared, and then we'll use that same rolling without slipping condition where v is equal to omega times r, so we rearrange that to v over r. This shows that my r squareds are going to cancel, and I'm going to have 1/2 times the mass of the wheel v squared plus 1/2 times the mass of the wheel v squared, which means my total kinetic energy for my wheel was equal to just m of my wheel v squared. The two halves go away because I'm adding two similar terms that each have a half as their coefficient in front of them. So now I can say, okay, well that means that the total kinetic energy for one of my bikes is going to be the kinetic energy of the frame, 1/2 mv squared for the frame, plus, then I've got two wheels, plus 2 mass of the wheel v squared. And that's my total kinetic energy. Now the problem gave me individual frame and wheel masses. The speeds now are going to each be 12 meters per second. So we can calculate the difference in our kinetic energies. I'll give you a second to allow you to pause the video to go back to work this problem. This also was problem 6 in the problems that we did in class on Wednesday the 22nd. So you can put those masses in, and if you wish to solve those yourself, you should then now come back to the video and see that you get 1010 joules for the first one and 1080 joules for the second one. So the first bike had a heavier frame. This one had a larger frame and lighter wheels. This one had a lighter frame but larger wheels. But we see that the total masses were the same. So we're seeing that when we are trying to optimize a bike in terms of efficiency, shaving the mass off of the wheels gives us a lower total energy, which means that we'd have to put less work into the bike to get it up to the same speed. Here, that same total mass, but with more massive wheels, takes more energy to get it moving at 12 meters per second, which means we're going to be tired faster, or it's going to be